Okay, Assalamualaikum and very good day. Okay, so let's continue with our lecture. So I will share the slides. Window. Hmm. Hmm. Screen. Okay, so can you see the screen now? You know the single phase circuits.
Yes, sir.
Okay, that's good. Okay, now, so for today's lecture, we are going to focus on the single phase circuits. This is a very important topics for you guys. Okay, so please be very attentive. Okay, so we will cover the sinusoids, the phases, the mass operations for the phases, and the transformations between the time and the phasor domain, the time domain and the phasor domain. So the objective for these lectures will be for you to able to convert or interchange between the polar and the rectangular form of voltage and current representations. Okay, for you to be able to do simple calculations involving AC currents and the voltages, such as I1 plus I2 or I1 minus I2. Okay, and then the most important part for you to be able to use polar and the rectangular forms to solve the AC circuits using the KCL and the KVL approaches. Okay, so now you can see that um, the circuits, it does not just contain the resistors but also the capacitors and the inductors. Okay, so you have to be careful, but the way you solve this is still the same, using the Kirchhoff's current law and the Kirchhoff's voltage law, and subsequently employing the Ohm's law. Okay, sinusoids. So sinusoids, they are coming in a sinusoidal wave, in a periodic cycles. Usually, they are expressed in this format: Vt, voltage, function of time, equivalent to Vm, the amplitude, sine omega t. Omega will be the angular frequency. So the amplitudes will be the Vm. They are using the positive part. Okay, and this amplitude will range from the negative of that value to the positive of that value. Okay, negative Vm to positive Vm. Okay, so if you're looking for the peak to peak voltage, PEAK, peak to peak voltage, VPP, that will be equivalent to 2 Vm. Okay, positive Vm minus negative Vm becomes 2 Vm. So that will be the peak to peak voltage. The omega, the expression for it will be 2 pi over t. T is the time for one cycle. And you also can express in the forms of frequency, 2 pi f. Remember this, guys? Omega equivalent to 2 pi f. And the argument will be omega t. So what is this argument? We are not arguing lah. What is that is, this is the premise whereby if you want to find the instantaneous voltage, you can use this value. Example, if I want to find, okay, what's the voltage when t equals to some value, let's say 1 second. Let's say 1 second is over here. Okay, so you will put the t equals to 1 second, multiply with omega, get the sine value of that, and then multiply with the Vm. you will get the V at the particular time. So the Vt here, the small case v, is the instantaneous value. Instantaneous. At that current time, what's the value? Okay, so it is a function of time, and this time the argument is the omega t. Okay, so the cycles, either you can choose from the crest to the crest, or from the trough to the trough, or from 0 to 0. So it should be one complete cycles where you have the positive and the negative side. Okay, so now let's say sometimes you also can have some phase difference pi. So this should be Vm sine bracket omega t plus phi. So this shows that the wave has started earlier by phi, the phase. It has started earlier by phi. Okay. And then you can keep continuing. The rest is still the same. Omega still 2 pi f, and the argument still you have omega t. Of course, you can just express the period time equals to 2 pi over omega, and the cyclic frequency f 1 over t is a reciprocal between the time and the frequency. Okay, comparing the sinusoids. So when you have two or more sinusoids of the same frequency here means the omega. Okay, omega. If they are same frequency, they could be either in phase or out of phase. Okay, example, you have here V1 equals to Vmn sine omega t, and you have V2t equals to Vm2 sine omega t. So in this case, if you want to know whether they are in phase or not, you will look at the one in the bracket, omega t. So they are the same. So we can say that they are in phase, provided this value of omega for the two sinusoid waves are the same, and they should be the same if you are comparing it. If you have different values, let's say this is omega 1, this is omega 2, then you can directly compare. Okay, you cannot directly compare it. We have to do some alteration so that the omega will be the same. Then we can check whether they are in phase or out of phase. So if you check the arguments and they are the same, we can say they are in the same phase, and there could be there are some chances that the amplitude are not the same. The Vm1 and Vm2, they could be different. Okay, they could be same or they could be different, so that doesn't matter. The only thing matters to know whether they are in phase or not will be the omega t, the argument. Okay, now example of out of phase. The out of phase will be something like this. You have omega t and you have omega t plus phi. So this shows that the second wave has started earlier. So you can see that in the graphical representation. Okay, the second wave has started earlier, before the zero, by a certain angle, phi. Okay, and then when you reach the maximum value, then only your V1 is start to happen. It is increasing, while the Vm has reached the maximum and then now going to 0, while your V1 is starting from 0 and then increasing to the maximum. So in this case, if you want to describe the relationship between the V1 and the V2, you can write in either of these two formats, such as V2 leads V1 by phi. Okay, you can say that, or you also can say that V1 lags V2 by phi. Phi is the angle. It can be any angle there. By look of it, okay, by the look of it from here, this phi could be 90 degree, because only in the 90 degree you will have this type of condition. When one wave is zero, another wave is at the maximum. So usually that phase difference will be 90 degree. But don't worry, usually those values will be given. Okay, and if I ask you to make some conclusion, you can write in this format. Okay, so logically, if omega t minus phi, that shows that it is starting after certain angle. Okay, so that means the relationship between the V1 and V2 for omega t minus phi, that will be V1 leads V2 or V2 lags V1. Okay, in this case, omega t plus phi, it will be V2 leads V1 by phi, or V1 lags V2 by phi. Either one of these two statements is correct. Okay, the next thing, phases. Those sinusoidal waves, they can be expressed in terms of phases. Why we are coming up with the phases? Because it is more convenient to deal with as compared to the sine and cosine functions. So this was introduced by mathematician Charles Steinmetz in 1893. So that was a long time ago. So these methods involve manipulating complex numbers. And complex numbers, they are usually expressed in this format. Okay, observe, z equals to x plus minus jy, where the j is the square root negative 1, the imaginary. So the j stands for the imaginary value. The real value, we just have the integer. It could be a round integer, or it can be a fraction, so it can be in any format. Okay, x should be the real value. J will be the imaginary value. And j is square root negative 1. Remember this. J equals to square root negative 1. In some cases, we also interchangeably use the symbol I. Okay, this J we use I. It is also correct. No issue. As long as we know the meaning of it. Even if you use your calculator, I mean the normal calculator such as Casio FX 570MS, the symbol they use for imaginary value is I. They use I. So no problem. It can be J or it can be a I. As long as, remember, we know that represent imaginary values. Okay. There are three common ways to express the complex number z. It can be in a rectangular form, x plus jy. Polar form, z equals to r angle phi, the value of the angle. Or in the exponential form, z equals to r exponent j phi. In your case studies, we will use these two, rectangular and polar. We don't use exponential. Okay. All of these three, they are interconnected with each other. Okay, now let's see what's the relation between the rectangular and the polar. Okay, so if you draw the rectangular values in a Cartesian coordinates, it will be looking something like this. Okay, this is the most simplest one for z equals to x plus jy. X plus jy. Both components are positive, so positive x, positive y. The imaginary values should be on the y-axis. Okay, and then you can find the radius, the hypotenuse. Okay, it's a rectangle, it's a triangle, and then you can find the angle from the real axis. Okay, so if you want to find what is your r, that will be using the Pythagoras theorem, x square plus y square square root. Okay, and the phi will be tangent inverse y over x. Okay, now guys, this is where you have to listen very carefully. You have to check your calculator first before you key in the values. If you have your calculator with you now and you open it, you turn on, you will see that usually in the default mode setting, in the default setting, you will see a small letter D there, capital letter D. That means it is in the degree. Okay. If you put all the values in radian and you use the degree to find, you will get a wrong answer. So you have to be careful. If you're using radian, then you need to change the mode. So usually you can click the mode button, okay, and then you can choose the radian. Then we change to R. So simple details, but you will fall very hard if you overlook. Okay, always remember that. That's why I'm highlighting this now. Okay, the fee here is where sometimes you will make mistake. So whenever you're using your calculator, check first what mode that you are currently using. Is it degree or radian? And then look at your calculations and then adjust accordingly. Okay, and the relationship between the x and the r will be x equals to r cos phi, and the y will be r sin phi. So essentially, this will be the link between the rectangular and the polar. X plus jy rectangle, r angle phi, the face angle, and the conversion, r cos phi plus j sin phi. Whenever you are in doubt, just draw this diagram and then check accordingly. Okay. Anyway, when you are doing your assessment like quiz, test, EA, you can open up the slides. So that's a relief there for you. Okay. But just be very careful. Okay. Now the addition and the subtraction, some simple mathematical analysis. If you have two complex numbers, Z1 and Z2, if you want to add, just use the rectangular form. Similar with your subtraction. You just add the real part at one hand and the imaginary part on the other hand. Okay? Subtraction, arrange all the real numbers at one side and then the complex number at one side, and then you do the mathematical addition and the subtraction. So you should know that it is easier to perform addition and subtraction of complex number in the rectangular form. Okay, that's the main idea here. As for multiplication and the division, it will be easier if you do these two tasks, multiplications and the divisions, in the polar form. Okay, so if you have the polar form here, R1, Phi1, R2, Phi2, and if you're doing the multiplication, just multiply the value, the amplitude's value or the radius, R1, R2 directly, and then you just simply add it up. For multiplication, you just add up Phi1 plus Phi2. If it is a division, you just divide the R1 over R2, while for the angle, you just minus it. Phi1 minus Phi2. Okay? So these are the four usual mathematical analysis that we usually use. Addition, subtraction, multiplication, and the division. For the first two, addition and subtraction, for complex numbers, it will be easier if you use rectangular form, while for multiplication and division, it will be easier if you do it in the polar form. But there's another way to solve any of this. Use your calculator. Simple, direct, provided you know what you're doing and you have to do correctly. Okay, next will be the phasor representation. Okay, if you have the waves, the sinusoidal waves, Vm cos omega t plus phi. So the phasor representation will be V equals to Vm, the amplitude, and then the phase angle, phi. If this phi is 0, just put 0 over here. Okay, no need to worry. If 0, if it is Vm cos omega t, that means Vm angle 0. That's it. The omega won't appear in the physical representation of phasor form. Okay, so this is the direct translations or the link between the phasor and the sinusoidal waves. So example, if it is 0, then you are lying exactly on the x-axis, and then you will now rotate anti-clockwise. Huh? So let's say you go to 30 degrees, so this will be the 60, okay, this one 90, the maximum value 90, and then you go to 120, then 150, then you return back to 180. So we will now on the x-axis, but on the other side. Okay, and then you keep on moving until you make one circle. Okay, so just imagine if you have, let's say, 5 waves, and if you try to analyze by drawing all 5 of them, it will be really difficult for you. Okay, if you draw all of the 5 and you represent it in a single phasor form, you will just see 5 lines. Okay, just 5 lines according to the phase angle. You just draw it, then it can be easy for you to analyze. So that's why we engineers, scientists, we try to make complex thing easier. Why? Easier to analyze, easier to understand, and easier to explain. That's the main reason for it. We have this phasor representation. So embrace this concept, guys. Okay. So this is the example. Okay. This example whereby they are representing the 3 different waves in the phasor form, and all of these are in the multi-phase, meaning you have a different phase angle, but same angular frequency, same omega. You must have same omega when you are adding, subtracting, multiplying, or dividing, or more than 2 sinusoidal waves. Remember that, huh? You can have a various phase angle. This, you can 5 or even 10 of them, and different phase angles. Doesn't matter. The only thing matters is the omega here must be the same for all 5 or 10 waves if you have it. Normally we won't go until that lah. Okay, the next, the impedance. Actually, this term is wrong. I mean, if I go by technical, it is correct. We can accept that, but the actual term for individual capacitor and inductor, the term should be reactance. Jot it down, guys. Reactance. R-E-A-C-T-A-N-C-E. React. React. R-E-A-C-T-A-N-C-E. Reactance. Okay, for individual capacitor and inductor. Impedance is a term for when you have a combination of resistor and capacitor and or inductor. Okay, combination of them. The resistor must be there as well. Then you can call it as impedance. So the impedance or the reactance for capacitor will be the symbol is not Z lah, it should be X. XC is negative J1 over omega C. Or if you want to put the J at the bottom side, then it will be 1 over J omega C. If you put at the upper side, it will be negative, bottom side, positive. What is omega? 2 pi F. What is C? The value of the capacitance for that capacitor. For reactance, inductive reactance, XL will be J omega L. What is L? The inductance value. What is the unit for the reactance? Ohm. Similar to your resistance. So now you have resistance for resistor. Okay, resistance for resistor. And then you have reactance for capacitor and inductor. So you have two reactants. It also means how much the capacitor and the inductor is resisting the flow of the current. That's why the symbol is ohm. Okay, resistance, reactance, the symbol is ohm. You combine both resistance and reactance, it will become impedance. As the name implies, it impeding what? Impeding the flow of current. The symbol will be Z, unit will be ohm. Okay. Okay, now we look into the time domain and the phasor domain. Okay. If you have something like Vm cos omega t plus phi, this will be the time domain. You have the time. The voltage is dependent of the time. If it is a phasor domain, it will be only using the amplitude and the phase angle. That's it. Example, Vt 6 cos 50t minus 40 degree. So the phasor representation will be V equals to 6 angle negative 40. That's it. Check the negative as well. It shows that it is starting after 40 degree. Another example, I function of t 5.38 cos 12.40 plus 17.4 degree. Then if you want to express this in the phasor domain, it will be the amplitude 5.38 angle 17.4. Okay, the frequency omega, the angular frequency, it does not appear in the phasor. Second, when you're doing the analysis for these values, the omega must be constant, must be the same. Meaning, if you want to find what is Vi, multiplication of V multiplied I, the omega should be the same. If the signals, meaning you have a different omega, the phases cannot be used. Okay, and another important part is the time function must be expressed in cos, in a cosine form before the transformation from time domain to phasor domain. Okay, if you have sine, you need to change it to cosine. How to do that? You have learned it in additional mathematics, trigonometry, sine and cosine identity. Okay, so you need to recall that back for this purpose. So what are the differences between the time and the phasor domains? Vt is the instantaneous representation, the instantaneous value at that particular time, while V will be the frequency representation, is the whole value. Why we use that? Because if you want to analyze, this will be the more simpler form. You can look at it directly. Here you have what? 1, 2, 3, 4 components. Here only you have 2 components. Okay. The simplification is to do the analysis easier. Vt, the instantaneous voltage, is the time dependent while the V is not. Vt always real with no complex terms while V is generally complex. Why is a complex value for phasors? Just look at this. This example, V equals to 6, angle negative 40. How do you express this in the rectangular form? 6 cos negative 40 plus j 6 multiply sine negative 40. So you will have the real and imaginary value. So when you have a real and imaginary value, it is known as complex format. This one, this one, guys, r cos phi, r sin phi. Okay, some example. Let's add this I1 and I2. The given I1 is 4 cos 60 plus 30, and the I2 is 5 sine 60 minus 20. Okay, so we can take our first current and try to represent it in the phasor form. So that will be the amplitude for degree 30. So for 30 degree equals to I1. Now let's look at the second current. It is given in the format of 5 sine 60 minus 20. Remember, the time function must be expressed in positive cosine form. Positive cosine form before transformation. Now this is in the sine form. So we need to change into cosine. How to do that? You have to minus with 90 degree. Okay. So if you do that, this will change from sine to cos. Remember the cosine identity like cos A minus B. If you are expanding it, will be what? Cos A sine B plus sine A cos B. Okay. So if you do the expansion for this, making 60 minus 20 as the A and the B will be 90, you will get this format back. That's why it is named as cosine and sine identity. They are linked with each other. Okay, so I don't have to go through that into that detail much. So please do revise on your own, guys. Please, So how you change the positive sign to cos, you minus 90 degree. So now you will have 5 cos 60 minus 110 degree. Now you can represent it in the phasor form. Take the amplitude, take the phase angle. 5, negative 110. So now you have done this, you also need to check a very important thing. Is the phase angular frequency the same? Okay, if you look at it, 60, 60. Okay, that's good. That's good enough. They are the same. So now you can proceed to add. Okay, so now you can do the addition, and we know that to do the addition, it is good to express the values in the rectangular form. So that's why they are changing to rectangular form. So 4 cos 30 plus j 4 sin 30 plus 5 cos negative 100 plus j 5 sin negative 100. And then now you got all the respective values. Arrange the real values and the complex number, and then you got the value. Now you can change back to the phasor form. If the question asks you express the final value in the time domain, you can do that as well. Just check the amplitude 3.22 cos 60 remains, the angular frequency remains, and then you look at your phase angle negative 56.97, so you just put up there. So now you got back your final value, which you have added up I1 plus I2. Okay, you have to do this slowly, and then what we say, once you are familiar with this, you can directly use the calculator. It will do the function for you, but of course you have to remember, most of the calculator that you have, they are not smart. Okay, they are not smart. You are the smart one. Okay, so I mean to say, if you key in the wrong numbers, wrong way, you just calculate from what has been given. It doesn't have the faculty to think and then make assumption. We are not, the calculators won't do assumption for you, so you have to be careful. Bend the calculator to your will. Understand that, eh? So you have to be very careful. Looks simple, but there are traps here and there. Okay, the nodal analysis. We are now moving into the analysis of circuit. All of the slide that I have shown you previously is to prepare for this. This is the actual one. All the stuff that I was talking for like 45 minutes or 40 minutes, many of those stuff you actually have learned. You have some understanding. You are aware of it. So now we are just trying to refresh that. So this is the most important part here. Okay. Current available can be applied. Okay. Whatever it is, if you need to find either the current, impedance, or voltage. Okay. Not necessarily just the current. If they give you current, they also can ask you to find the impedance. Okay. So either one, impedance, current, or voltage, you can use the nodal analysis or the mesh analysis, of course. Okay. So for nodal analysis, how do we do? Total current going in equivalent to total currents coming out. And the node of reference must be having different current coming in and different current going out. You cannot just simply choose any nodes. The reference nodes must be a proper one. Once you have chosen, write down the equation, the relationship between the currents. if let's say we have chosen the node V2, so the current in will be I1 and the current out will be I2 and the I3 based from the given direction. So you have I1 equals to I2 plus I3. From this, now you can develop it into a Ohm's law function. So what is I1? From the beginning to the ending. V1 minus V2 over Z1. What is I2? V2 minus V0 over Z2. V2 minus V0 over Z2. What is I3? V2 minus V3 over Z3. So how to choose which voltage comes first? Starting, ending. From the starting to the ending. I1 meaning V1 minus V2 and it passing through Z1. So you put the Z1. Now you got all of this, you can solve. Example. Okay. For your quiz, it will look something like this. Okay. So now you have a given voltage source and you have a this will be known as independent voltage source. This will be known as dependent current source because it is dependent of a current flowing through in the 0.1 farad capacitor branch, depending on that. So the diamond shape for the source, either voltage or current, that means it is a dependent source. If it is a circle, either for voltage or current, it will be known as independent. It supplies its own source. Okay, let's say you are given this type of question and what they're asking you. Okay, now they're asking you to find the Ix. Okay, so let's go through slowly. Let's say you have to find the value of Ix. Okay, so the first thing is do the basic stuff first. Don't simply go dive in unless you know what you are doing. Since you are starting now, so do it slowly. That will be the proper way. What you should do, try to represent all of this in the phasor domain. So for your power source, it will be V equals to 20 phase angle 0. Second thing, after you've done all of that, change the inductor and the capacitor to reactance value. It should be in the ohm. Uniformity. Remember this, guys, uniformity. The unit must be uniform. Now you have ohm, you have Henry, you have farad. They can't meet with each other. Okay, must be synchronized. So how to convert the inductance value to reactance? XL equals to J omega L. J omega L. Now, where is the omega? In the power source, 4T. So your omega is 4. So J omega means J omega L means J plus omega, which is the value 4, multiply with 1. So you have J 4 ohm. Then do similar for your second inductor, J omega L as well. So J multiply with omega, which is 4, multiply with 0.5, you will get J2 ohm. And then you do for your capacitors. So what is the expression for capacitive reactance? Negative J over omega C. Negative J over omega C. So you have 1 over 4, omega is still the same, multiply with 0.1. So it will be negative J 2.5 ohm. Okay, so now this is your first step. Make this one clearer, and then you can redraw the circuit. Okay, put up all the values. Okay, now you can use your nodal analysis since they ask you to do the nodal analysis. So here you have two nodes. Okay, so let's look at the first node. Yeah, let's say this is your I1, this is your IX, this is I2. So I1 equals to IX plus I2. What is I1? 20, 0 degree minus V1 over 10 ohm. 20 minus V1 over 10. Okay. What is my Ix? V1 over negative J 2.5. V1 over negative J 2.5. You have to incorporate the J value. I2 is V1 minus V2 over J4. Okay. Now you can just do some simple manipulation and then you will get this expression. You have to try this. 1 plus J 1.5 V1 plus J 2.5 V2 equals to 20. Okay. And then for your second node, it will be I2 plus 2ix equivalent to I3. So what is your I2? V1 minus V2 over J4 plus this 2ix equivalent to V2 minus V0, which is 0, over J2. Okay, now you can do the manipulation. You will get 11 V1 plus 15 V2 equals to 0. And you can take note that your current Ix is V1 over negative J 2.5. Okay, now you have two unknowns, V1 and V2, and you have two equations. Now you can solve. Okay, do the factorization. You may take V1 as your title, then it will be V1 equivalent to negative 15 V2 over 11. Then substitute, you do the rest, you do the math, you will arrive at this value. V1 equals to 18.97 degree, 18.4 degree. Okay, now you got your V1. Our primary objective is to find the Ix. So what is Ix? V1 over negative J 2.5. So we know our V1. Plug in the values, divide it, you will get the final answer. 7.59 degree 108.4. So now you can express this in the time domain. Take the amplitude, put the cos 4t, this remains, and then put the phase angle plus 108.4 degree. That's it. Okay. So guys, please try to do this on your own. Okay, this value should be correct. You try yourself. I give you 5 minutes break. Okay. Please try.
Sir, are you talking right now? Because you're muted.
Yeah. Again?
Are you talking just now? Because you're muted.
No, 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 I'm not talking. I'm just scrolling. Okay, guys. I hope you went through with this problem. Try to get this final answer. Now, I have a question for you. If the question also asks you to do, to get the power absorbed by your capacitor here, so how to do that?
After we finish the calculation, I believe we can calculate the power from the current and voltage. Yeah.
Okay, okay, that's good. So what should be the value? What should be the value? What will be the V for this component capacitor? You all remember, right? The formula is P equals to VI, power. So what's the value of V here for this capacitor? Anyone? No one? Guys, are you here? Anybody wants to attempt that? What V will be at your capacitors? Negative J 2.5 ohm. What will be the V in this component? It will be the V1 lah. Okay, it will be the V1. because this is the V that directly coming across your capacitor. Directly. This V1 also could be over here, this branch. And this V1 also could be this whole of this branch. But of course, this will be a bit more complicated. And it is irrelevant for us because our focus is on the capacitor. So look at what voltage that is governing this capacitor. So it should be the V1. So what will be the current? What will be the current that is going across your capacitor negative J 2.50?
It should be the IX current.
Yes, it should be the IX current. So to answer my question just now, P equals to VI, what should be the value? 18.97 multiplied with
7.59.
7.59. Okay, what to do with 18.4 and 0 or 108.4?
We add it together.
Huh? Add it together. Okay, so this is where you have to be careful. Okay, I'm just jumping ahead lah. We will do this power analysis later, but I'm just jumping a bit ahead of that. The angle you have to take into account. Okay, but over here, this is the voltage and the current. Okay, so for the angle, we need to check the phase difference. How much phase difference between the voltage and the current? So in that case, what will be the phase difference between the V1 and the IX? Anyone? What will be the phase difference?
90. Yes.
Again?
90.
90 degree, or you can be a bit more technical, negative 19 degree. Okay, so 18.4 minus 108.4 will give you a value of negative 90 degree. Okay, what is cos negative 90? Anyone with calculator?
It's 0.
0. So the point here is there is no power absorbed at the capacitor. P equals to 0 watts. There will be no power loss or power absorbed at the capacitor or the inductor. All the power loss is on the resistors alone. Because this is coming from the triangle V and the I. Later we will cover that. So I'm just giving you some idea. If this type of questions comes up for your quiz, then you know lah. What is the power loss at the capacitor? It should be 0. Mathematically, you can prove it. Okay. For the individual capacitor or inductor, the power loss is always 0 because the phase angle will be always 90 degree. So it's either positive 90 or negative 90. The cos 90 will always give you a value of 0. So the P is 0 watts. The only power loss will be at the resistors. You understand?
Yes, sir.
Okay. So now this is just what we say summary. Complex number zx plus jy rectangular form. Polar form r the radius, the phase angle. Okay. So for if you have 1 over z, then it becomes 1 over r, the phase angle become negative. Okay, just inverse it. And 1 over j is negative j. And what is j? Square root negative 1. If you square root the impedance, the z, you will square root the amplitude and divide the angle by 2. And if it is a complex conjugate, if this is your complex number, and you are finding the complex conjugate, it will be minus x minus jy. If your given complex number is x minus jy, the complex conjugate will be x plus jy. Okay, and then from here you will get the polar form r negative phase angle. These are just the mathematical operations. Okay, so go over these slides and try to fully understand the concept. Okay, we will have our quiz next week, inshallah, most probably. If there are changes, I will inform you. Okay, so let's move into the second unit, the nodal and the mesh. These are just the same lah. Okay, the same thing. I'm just being very careful, revising this many times so that you can understand. Okay, example of this, for the nodal analysis, you see the current is going in for these particular nodes. So I1, I2, I3, I4, you just add it up, equals to 0. In this case, you have one current going in, two currents going out, different one or different, all are different. So I1 is I2 plus I3. Okay, depending on the current direction given to you. If it is not given, then you can make your own. Okay, usually to make my life easier, I will give the direction. I will give you the current direction. So you have to decide from there, so that it's easier for me to mark. So the way I mark, I usually look at the final answer. If it is correct, I just give the full marks, no question asked. If the final answer is wrong, then I will look at the steps. Okay, you already know this part. Yeah, we have done it. We have done this example just now. Okay, just go through again. Okay, just go through again. What I want to show you now is the mesh analysis, the another way of doing these circuits. So another refresher coming in. So let's say you have your voltage, you have impedance, okay, and then you need to get your mesh. So this will be your first mesh. This is going clockwise direction. As usual, the total voltage drop and voltage rise is equals to 0. That's the explanation for KVL, Kirchhoff's voltage law. And to make your life easier, start with the resistance. In this case, start with the impedance. So you make just one nice loop going over to your Z1. So the first point that it enters will be the positive. So it will be I1 Z1, I1 Z1, and then you move to your Z2 impedance. So it will be positive Z2 bracket I1 minus I2. I1 minus I2 multiply with Z2, and then you complete the mesh. Negative V1 equals to 0. So you move your V1 to the other side, it becomes V1 equal to I1 Z1 plus I1 minus I2 Z2. Okay, straightforward. And then you can move into your second mesh. Okay, you need to take into account all the components that it covers. So in this case, to avoid the ambiguity from the beginning, you may start with a impedance that only have one current flowing in. So you can make one nice loop goes to your Z3. So I2 Z3, I2 Z3 plus I2 Z4, I2 Z4. Then you reach over here. So this will be positive Z2 I2 minus I1 equals to 0. Okay, that's about it. And then now you can go on and solve the question. Okay, example. To solve this circuit by using mesh analysis. Determine I0 and V0. So where's your I0? I0 is the current going through a negative J2 ohm branch, the capacitor. And V0 is the voltage drop at the resistor 2 ohm. Okay, we have a independent current source and we have a dependent voltage source 3V0, meaning whatever voltage over here will be the voltage taken up by the current, the voltage source. Okay, so let's look and try to get the mesh. You have two mesh over here. So the first mesh, you may start with your J4 ohm. So this will be what? I1 J4, I1 J4. Okay, this one. And then you move positive 3V naught, positive 3V naught. And then you move over here 2 ohm I1 minus 4. Okay, 2 bracket I1 minus 4. I1 minus 4 ohm. I mean 4 ampere. Because this is the current moving in. That's why we didn't take this mesh. This mesh already have the current, which is 4 phase angle negative 30 degree. So we don't have to really do that. We just can focus on the two mesh. Anyway, we have two unknowns. You only need two equations. Okay, that's how you approach the problem. And then now you have the expression. Try to simplify it. Okay, try to simplify. Try to rearrange. You will get this. Negative 4 plus J4 I1 plus 16 negative 30 degree. Okay, you see here one in the rectangular, another one is in the polar. Okay, do the adjustment accordingly and then you will get your final answer. I1 is 2.8415 degree. So meaning to say you have to change this to
Rectangular
polar form.
Okay.
Yes, has to be in the polar form. And then you do the calculation. Of course, this is when you do by hand one by one. If you use your calculator, it can directly compute. But again, have to be careful. Put the bracket where it should be. Take note of the negative. Take note of the form that it is in. Okay, it is perfectly doable. I have done it. So the same thing applies to you. Again, provided you are very careful. Is I1 is the one that we are looking for? No, we are looking for I0 and V0. So the journey have to go on. Okay, so for mesh 1, my I1 is 2.8415 degree. So my I0 will be, you have to do the mesh analysis over here, negative 3V naught plus I naught multiply negative J2. So these are very simple equation. So you can rearrange as this. I naught equivalent to 3V naught over negative J2. Okay. And then you plug in the values for your I naught, for your V naught, sorry, which is 2 multiplied with your uh, for negative 30 degree minus I1, and then you will get your I naught as 8.4815 degree, and your V naught will be negative J2 I naught over 3, 5.66, negative 75 degree. Okay, this I can consider as a quite a straightforward and simple circuit lah. That's why you have to try this before you move on into more complicated analysis. Okay. Any questions so far?
So far, no questions, I think.
Okay. So again, please try. You have to practice this. You're gonna come across this many times. This is just a single phase. After this, you will have 3 phase. Okay. So please be very careful. Please observe this. Try to understand and internalize slowly, so that when things start to get complicated, it will be easier for you. Okay, so this will be the next one, also for single phase. All of these are actually in the same slide. It's just being divided into 3 parts. Okay, these are just basic elements that you are going to look into: the impedance, the components of impedance, the admittance, and the impedance combinations. So the circuit elements is just another revision. Common circuit elements, the most basic one will be the resistors, inductors, capacitors. Okay, so this will be the phase diagram. Okay, for a resistor. For a resistor. Right. Okay. Actual size. Okay. The new function. Okay. Okay. For voltage and current that are going through in resistors, they are in phase. They are always in phase. Okay, the magnitude will be different. The voltage is a bit higher than the current, but the phase difference is 0. Phase angle difference is 0. You see here, when the voltage is going to the maximum, the current is also going to the maximum. When the current moving to minimum, the 0, voltage also doing the same thing. So for a resistor, the voltage and the current, they are in phase. So when they are in phase, if you are going to draw the phasor diagram for resistor, you usually draw the V and I overlapping at each other. Overlapping at each other, and this will be the point that you are taking, either at this point, what's the value, or at this point, what's the value like, or any point. At any points, they are in phase. Okay, they are in phase. You can draw the similar diagram in the second quadrant or the third quadrant or the fourth quadrant. They are always in phase. V and I, they overlap. Okay, we have done this. The reactance, guys, remember reactance. Individual capacitor and inductor will be known as reactance. So what's the formula for reactance? Negative J 1 over omega C or 1 over J omega C, while the reactance for inductor will be J omega L. Symbol X. So XC and XL. Okay. So what is this? Phasor relationship for inductor. Okay. So now you have an example of current moving through the inductor. Okay. So the V, the voltage drop will be J omega L multiplied with the current, because now this is exactly like a resistance. Okay, understand? Eh? So example, if you have your Vt 12 cos 60t plus 45 degree, what you have to do? You have to represent this in the phasor form. Okay, observe the cos. If it is sine, you have to change by minus 90 degree. Okay, observe everything. So this will be 12 degree 45. 12 degree 45. Okay, that's good. And then now change the inductance to reactance. Okay, example, they're giving you 0.1 Henry. This is the inductance. So find the reactance. J omega L. J omega, you get it from your VT 60. This is your angular frequency. Multiply with 0.1. You will get J6. So 12 45 degree over J6, you will get 2 negative 45. So if you want to find what's the current flowing through your inductor, this will be the one, 2 cos 60t minus 45 degree. Okay. So you have your Vt 60t plus 45, and you have your IT 2 cos 60t minus 45. So what's the phase difference? 90 degree. 45 minus negative 45, 90 degree. So you will see that for pure inductor, you only have inductor, the current lags the voltage by 90 degree, or voltage leads the current by 90 degree. Where is it? Okay, inductor. Okay, V leads the current. V leads the current. So if you draw the current in the first quadrant for inductor, the V should be in the second quadrant. Okay. If you draw the voltage in the third quadrant, the I should be in the second quadrant, so on and so forth, because the rotation is anti-clockwise. Observe the arrow, guys, anti-clockwise. Okay. Always remember, for a pure inductor, the current lags the voltage by 90 degree. Next, for capacitor. Okay, another example, similar case, they have given you the Vt and the capacitance. Now you have to find the current. Okay, so it will be V equals to I multiply XC. Okay, so you have to find your XC first. So what is XC? Negative J over omega C. So what is your omega? 100. C is 50 micro. So you just multiply it, okay, and then you plug into your Ohm's law formula. Okay, you remember this is 1 over j omega c, right? That's why this is at the top, j omega c v. So your v is what? 6 negative 30 degree. So now you just multiply in, you will get 0.03 degree 60. So this will be the current flowing through your capacitor. So if you write back the voltage and the current, you will see that the phase difference is negative 90, or you also can say positive 90 degree. But the fact remains the phase difference is 90 degree. But in this case, the current will lead the voltage by 90 degree, meaning the current will start first, then only the voltage comes in. So for a capacitor, this is logical, because what does the capacitor do? It stores charges. It stores charges. So the current has to go first, accumulate the charge, then the voltage will be induced. So if you are drawing the phasor diagram for a capacitor, current leads the voltage by 90 degree for a pure capacitor. You also can say that the voltage lags the current by 90 degree. So if you draw the voltage for capacitor in the second quadrant, the current must be in the third quadrant. If you draw the V in the third quadrant, the I should be in the first quadrant, so on and so forth. Again, observe the rotation. It is anti-clockwise for a phasor diagram. Okay, for your phasor diagram. So to make your life easier, always choose one of these as your main component. It is advisable to use voltage lah. Meaning if you know the inductor, just draw the V, the I at the back. For capacitor, you draw the V, the I should be at the front. That's it. For remember this, the term for pure inductor and capacitor. The angle between them will be always 90 degree. For pure inductor, pure capacitor. Any question guys on this?
In later quizzes, will they ask us to draw the phase diagrams like this?
Again?
Will we be required to draw these phase diagrams later on?
Okay. It depends lah. It depends on the question.
Okay.
Okay. Normally, I mean, with all this online assessment, it is better if you could draw lah. Normal cases, it is not applicable, but for EA, yes. Extended assignment, everything has to be shown. Okay. Any other questions?
I don't think so.
Okay. So let's keep moving. Okay, impedance. Okay, now we're coming into the impedance. So you have the normal Ohm's law, V equals to IR, and it can be expressed in terms of reactance. V equals to J omega Li, and for capacitors it will be V equals to I over J omega C. The reason is that the reactance for your capacitor is Xc equivalent to 1 over J omega C, or negative J over omega C. So that's why it looks like this. If you're in doubt, go back to the basic. Okay, this is your Xc. So what is impedance? As I mentioned earlier, impedance will be a total combination of resistance and the reactance. As the name, impedance means is the opposition of the circuit to the flow of the current. Similar with your resistance. So for all of these, resistance, reactance, and the impedance, the units are ohm. Okay, so this is the resistor, inductor, and the capacitor. Okay, so the impedance combination of both resistance and the reactance. So in the case of X more than 0, the impedance is inductive or lagging, meaning the current lags the voltage. We can imply that just by looking at the impedance. If the X is less than 0, meaning negative, meaning you have R minus JX, it shows that the impedance is a capacitive or leading. Leading here means current leads the voltage. If the X is 0, it shows that the circuit is acting like a resistor. You may have the inductor and the capacitor, but when you do the analysis, the X becomes 0. It is perfectly possible. This shows that the circuit is acting like a purely resistive. So when does this happen? One case that this could happen is in the case of resonance frequency. In the case of resonance frequency, the individual reactance of inductor and the capacitor will cancel out with each other, leaving only the resistor as the active component. Okay, just another round of revision over here. So if you have an inductor, a short circuit at DC, so in this case the omega is 0. It's a short circuit. For open circuit at high frequencies, the omega is approaching infinite. Okay, omega 0 means short circuit, omega going to infinite means open circuit. For capacitor is the opposite. Omega 0 means it's an open circuit, omega going to infinite, it will be the short circuit. Meaning it is now at the it let the current flow at the highest value. Why? You see the relationship. 1 over infinite is 0. So Z0 means it is a short circuit. Okay. So omega 0 means 1 over 0 infinite. So Z infinite means the resistance becoming very high. So it is implying that the circuit has become a open circuit. Okay, straightforward. Any question on these two? Impedance of inductor at certain values, omega 0 and omega infinite for inductor and capacitor. Any questions?
For the impedance of the capacitor, does it matter if the capacitor is polarized or non-polarized?
Does it matter if the impedance is polarized or not polarized?
The capacitor, I mean, because the symbol for capacitor is the curved one in this case.
Yeah, it doesn't matter.
Okay, thank you.
It doesn't matter. Because now we are dependent of the frequency, the angular frequency. The angular frequency is the one that gives rise to the reactance. Okay, now admittance. Okay. Admittance is the reciprocal of impedance, similar to conductance. What is conductance? Conductance is the reciprocal of resistance. If resistance means how much is the circuit is opposing the flow of current, conductance will be how much the circuit is allowing the current or the electrons to flow. Okay, so for admittance, the symbol is Y equivalent to 1 over Z or I over V if you are expressing in the form of Ohm's law. The unit will be Siemens S or the inverted Ohm symbol, the omega is an inverted form, or S lah, Siemens. And the Y will be G plus JB. G is the conductance for the R, B will be the susceptance, the reciprocal of reactance. Now you have so many names, right? Resistance, reactance, impedance. So remember this, all of these are the resistance of the circuit to the flow of current. All these three things: resistance, reactance, impedance. All of this symbol ohm. The reciprocal will be conductance, susceptance, impedance. Admittance. Admit. Okay. So what is this? Example of impedance calculation. Okay. Okay, now you have a very simple circuit. You have a one single voltage source, one resistor, and a capacitor. Okay, good. So find the VT and the IT in the circuit shown. Okay, the V and the current. Okay, so first you have to find your total impedance. Okay, you can find the total impedance 5 plus 1 over j omega c, and then you can simplify it, put up in the rectangular form 5 minus j 2.5. But of course now you have to change this into polar form because you are going to do the division. I equals to V over Z. So V is tan angle 0. There's no angle. Omega is 4. So you do the math, you will get this value 1.79, 26.6 degree. So this will be the current flowing through the circuit. Okay, at any point of time. This is the instantaneous current. If who's the guy? Okay, if you are looking for the voltage at the capacitor, similar Ohm's law, take the current, multiply with the reactance, not the capacitance. I have seen some students, they have done nicely over here, get the current, the correct current, but when we ask them to find what's the voltage drop at the capacitor, they take the current 1.75 multiplied by 0.1. You see, all the hard work is gone. You have to multiply with the reactance, not the capacitance. So you have V equals to I ZC. What is ZC? 1 over J omega C. Okay, J multiplied by 4. 4 is the omega. Multiply 0.1, the capacitance. Then you do the division, you will get this value. So this will be the voltage at the capacitor. So now, if I ask you to find what is the power loss or power absorbed by the capacitor, the answer must be, what should be the answer? 0, because the phase difference is 90 degree. So cos 90 is 0. Cos theta here is the power factor, which we will cover in detail, but I would like you to be aware of that. The power loss is only at the resistors. Okay, next, impedance in series. If you have the impedance in series, you just add it up and get the Z equivalent similar to your resistor. Z1 plus Z2 plus Z3 plus until the Zn. So that will be the Z equivalent. While if it is in parallel, similar, 1 over Z equivalent, that will be 1 over Z1 plus 1 over Z2 until all the components are covered. Or you can be fancy now. You can be fancy, no problem. You can express all of this in terms of Y, admittance. So that will be direct one lah. Equivalent admittance Y EQ will be Y1 plus Y2 plus Y3 direct. And then when you got your Y equivalent, you just inverse it to get your equivalent impedance. The values must be the same. Okay, the values must be the same. Okay, find the input impedance Z in. Okay, now guys, I give you like 5 minutes. Please try. The answer is already there, but I want you to try. Take a piece of paper and your calculator and start doing it. So when you have this type of circuits, the first thing that you should do is to change all of these components to reactance and resistance only. Symbol ohm for uniformity. Okay, you cannot solve this by only taking this value directly. You can't. That will be wrong. Okay, so now you can change all of these components. So for your Z1, it only consists of the impedance. I'm sorry, capacitor 2 millifarad. So get the corresponding reactance. For your Z2, it consists of two components, resistor and a capacitor. So it will be 3 plus 1 over j omega c. Omega is 50, multiply with the c 10 millifarad. You will get 3 minus j2 omega or ohm lah. Then the Z3 consists of two components as well, inductor and a resistor. So 8 plus j omega L, j50 multiplied 0.2, you will get your Z3. Then you can redraw this circuit, okay, and then you will see that this branch and this branch, they are in parallel. So you do your parallel analysis. 1 over 3 minus j2 plus 1 over 8 plus j2. Do the multiplication and the addition. Finally, the division, you will get 3.39 negative 18.3 degree. So this whole thing now done. So that component will be in series with your Z1, meaning you can now change to rectangular form and then just add it up. And the final answer will be 11.53 negative 73.8 ohm. So that will be the Z equivalent lah, or input impedance for this particular circuit. Any question on this?
So far, I don't
Please.
think so.
Okay, please try. Please try. Okay. Example 2. Okay. Okay, guys. I will leave this to you to check. Okay. Please go through this example. Now, before we end the class, do you have any question? Any question, guys?
The quiz for next week, what day will it be on, sir?
The focus of your quiz,
Yeah.
it will cover until what we have discussed today.
Oh, okay.
Okay. All the circuits analysis using KVL and KCL and the Ohm's law. Resistors, capacitors, inductors, so on and so forth. So I'm intending to do the quiz on Thursday around 9 a.m.
It'll be open for 1 hour or?
The quiz should be simple lah. Maybe I will give you 30 minutes.
Okay then, because on Thursday we have a tutorial at 11, so yep.
11, okay, should be fine lah.
Yeah.
I will start around 8:30 or 9.
Okay.
Maybe we finish by 10. Okay. So please go and revise. Remember what we have covered. We also have covered the power loss, the power loss or power absorbed in capacitor, inductor, and the resistor. Remember, capacitor, inductor, the power loss is always 0. For resistor, yes, you will get the value because they are in phase. Okay then. Thanks for coming by. See you again next week, inshallah. And don't forget to put your name for your group project.
All right. Thank you very much, Doctor.
Okay then. So let's end our class for today.
Thank you, sir.
Okay, you're most welcome.
Thank you.